In this video, we're going to discuss rate laws in more detail. Let's look at a reaction. We have H2 gas plus I2 gas going to 2HI gas. If we were to plot over time, the concentration changes. Well, let's just go ahead and use H2 up here. And we'll start with our HI down here. At the very beginning, I have no products and I have all reactants. What will happen to our H2 is that it will decrease over time. It'll start to go down, down, and down. However, it tapers off. It doesn't decrease consistently. It doesn't go in a straight line. It will curve. In this initial unit of time, it will decrease by so much, but in a later unit, same amount of time, it won't decrease by nearly as much. The difference from start to end will be significantly different. How much of our material disappears in a set amount of minutes or hours or seconds can change depending on when in the reaction we are looking at it. Early on, we tend to see stuff disappear more quickly than we do later on. What's happening to our product? Well, it's actually going to climb faster. Think about why for a minute. For every time we lose one H2, I've made two HIs. And so the change at any given amount of time for HI should be twice the change we see for that same amount of time for the H2. Not perfectly to scale here, but the idea is that my HI is increasing faster than my H2 is decreasing. Well, this has to do with how much of the product is used up and how much is created as the reaction goes on. But why do they slow down as time continues? Well, part of that was concentration. As we run out of H2, as we get less, there's just less chances it can ever go find an I2. As a result, there's less collisions, less chances for a reaction to happen, fewer reactions per second. So when we think of rate, since rate is usually the change in our concentration over the change in time, how we measure our rate actually depends on when during the reaction we are measuring it. You could average it over the whole time, and you'd find a rate that said, I changed by this amount in this amount of time. But if you'd done the rate at the beginning, you'd find that you actually reacted more quickly. If you'd measured it somewhere in the middle, you'd have some middle range. If you measured it at the end, you'd have some slow rate. So what does it mean to be the rate of reaction? We actually have different rates. We have average rates, we have initial rates, we have rates at any arbitrary 2 points during our time of committing this reaction. As a result, we need to know what it is we're trying to talk about. And often what we'll do is we'll talk about initial rates. Initial rates are if you were to follow the tangent of the line right at the beginning. How fast are you decreasing right at that moment that you begin? There's various spectroscopic and electrochemical ways to test a very brief amount of time early on to see how much is reacting. The idea is this prevents any complicating factors like the products breaking back into starting materials or other such situations. This is the least complicated moment, and so it's the rates we tend to focus on. Well, how do we go about calculating that? We'd need some data and find changes in concentrations over small periods of time at the beginning. But in the end, we need to tie it together because there's different chemicals. They can be at different concentrations, and they all can interact with each other. This is where a rate law comes in. Really just an equation that says that the rate is going to equal some constant for the rate times the concentration of your first species to some power times the concentration of your second to some power, and so on if you have more species. K is our rate constant. Concentrations of A and B will be the concentrations of our chemicals, and X and Y are the orders. These are not the coefficients. They're not 2 or 1 from our reaction up above. These are based on the process by which the reaction occurs, the mechanism, which we'll describe more later on. But the order in which certain chemicals have to interact, break bonds, rearrange, affects the rate of reaction. And that is what X and Y represent. These cannot be determined except experimentally. You cannot look at a balanced reaction and know what the rate law orders will be. So experiments have to be performed to determine them. Well, what can they come out to be? Well, a chemical can be first order, which just means its exponent is 1. So say X equals 1. It could be second order, in which case it would equal 2. It could be third, it can be honestly a half or negative. They have different effects. Generally, things tend to be first or second, occasionally zeroth, where they just don't matter. Sometimes one chemical concentration doesn't matter. The speed of the reaction is determined completely by other chemicals. They have to do their thing before they will find the thing to the zeroth order. And so the rate limiting step, which will come up again in mechanisms more, but the step at which anything past doesn't affect the rate law, sometimes the chemical doesn't show up till past that step. And so in that case, sometimes our exponent is 0. The concentration doesn't affect the rate. So how do we determine what the actual order is for each chemical, and therefore the overall order, the sum of the individual orders of the rate law? Let's see that in our next video as we practice it.